Let's start on time.
Can you see my screen?
Yes, we can see the screen, full screen, and hear you.
Yes, great.
Yeah, 1 more minute. So I think it's time now to start this session, which is practically, I would say, the first real school lecture.
Jota, I can't hear you. I think that...
You cannot hear me.
Okay. Can the others hear me?
Yes.
Can someone say something?
Yes, Maurizio, we can hear you. We can hear you.
Marius.
Yeah. We can hear you. You cannot hear us.
Is it a problem with my audio? Because yes, but you can hear me, right? Yes. Okay. So I will have no feedback from your side, apparently, for some reasons. So that's I don't know why my audio has disappeared all of a sudden. All right. Anyhow, I start. Okay.
Yes.
Yes. Okay. So, good morning from Geneva, Switzerland. So I'm giving this presentation, this lecture from my office at CERN, and I'm particularly pleased to address to a wide community. So it's just one of the advantages of the virus, actually, of our crisis, is that we are using these modern technologies, and we can open up to many more people. So welcome to our community. It's really a pleasure to talk to such a wide audience. And I was thinking that to start this presentation, this lecture today, you needed an introduction to particle accelerators, because we are going to have a lot of information about how particle accelerators can be used for the treatment of cancer, but we should really tell you something about how an accelerator works. And in this lecture, I will try to go through some subjects without any mathematics, without formulas, just to try to be as simple as possible. First of all, we want to build particle accelerators. What do we need? We need a particle and we need an accelerator. Where can we find the particles? This is very easy, it's in the atoms. In the atoms, we find particles, and we are going to take charged particles, because we want to accelerate particles using electric fields and deflect, guide, deviate particles using magnetic fields. Magnetic fields can never give energy to a particle. They can only change their trajectory, while electric fields are used to give energy to the particles. Charged particles can be protons, of course, can be electrons, but also can be charged nuclei. Charged nuclei, that means that you take the atom, you take off the electrons, you strip off the electrons, you leave only the nucleus, and this is this behaves like a particle that can be accelerated. It is an ion. And you have to understand that there are many differences between the different types of particles. Electric charge, so electrons and protons have the same charge, identical, unit charge, but ions can be much more charged, because it's a nucleus with many protons. They have the charge of the protons. In terms of mass, electrons are very light, and protons are heavier, and ions can be much more heavier. The difference in mass between electron and proton is about a factor 2000. So it's really it's a huge difference working with electrons and working with protons. And once we have started our acceleration, what can we do with these particles? We have to understand that particle accelerators can concentrate huge amounts of energy into tiny little volumes. Particle accelerators are actually our tool, is an instrumented accelerator that is used to access the subatomic dimension. The only way for us to interact with the atoms and to interact with the nuclei. Why? Because, for example, let's assume that we accelerate a proton in an accelerator. This proton is sent to a target, to some material, and interacts with the atoms, smashes on the atoms of the material. What happens? First of all, it will flow through the cloud of electrons that is around the nucleus, and we give energy. We give energy to the electrons. And then if the proton has enough energy to go through the barrier that is formed by the electrons, we can smash into the nucleus if we are good enough to hit the nucleus, and then we'll give energy to the nucleus. So a particle beam will give energy to the atoms of a material where it is sent to. This material can be a metal or can be a patient, can be a human on which we send our particle beam. What is special in this particle beam is not the energy, it's the density of energy. And here in this slide, I compare 3 cases which are quite interesting. Let's take a proton that comes out of the Large Hadron Collider, which is the largest accelerator ever built in the world, which is actually under my feet in this moment in Geneva. It is still under commissioning, it's not yet operating. But what is the energy of one single proton out of the LHC? Actually, it is very, very small. Only 10⁻⁶ joule of energy, which is nothing compared to the chemical energy, for example, that you have inside a pot of yogurt that you can. So if you go to the shop, you buy some yogurt, you will read on the label, it is written certain number of joules into the yogurt. Is the energy of the chemical bonds inside the yogurt. This is 10⁵ joule. It's 11 orders of magnitude higher than the proton out of the LHC. So why should we accelerate protons in the LHC? We should accelerate yogurts. No, it's not so easy. If you consider, for example, something which is even more energetic, is a train. Take a high-speed train, and you will get 10⁸ joules, so even more energy. But what is the difference? The difference is the density of energy, because a proton is very, very small. If you take the classical radius of the proton, we have the density of energy is 10⁻38 joules per cubic meter, which is enormous compared to the yogurt, only 10⁹. And it's also enormous as compared to the train, which is better than a yogurt in this case. And the train is 10⁻11 joules per cubic meter. So you see, this is kinetic energy, chemical energy, and energy, which is also kinetic, out of a particle accelerator, but on a subatomic scale. So accelerators are unbeatable in concentrating huge amounts of energy in small volumes. And how can you use this energy? You can smash these particles against other atoms, other nuclei, and then you can break the nuclei and you do nuclear physics. Actually, in this way, you can modify the elements. You can convert lead into gold. That was the dream of the old alchemists. And nuclear physicists are the alchemists of modern age. Or you can do particle physics. Like in the Large Hadron Collider, you can collide together 2 protons with such an amount of energy that a lot of particles that do not exist freely in nature are generated, and then you can create the bosons, the quarks, and you can do particle physics. Or something that also is very important for you to understand at this stage is that this energy in a particle beam can be also used to generate new particles and produce secondary beams. The most typical use of typical secondary beam is a beam of photons, X-rays. You can produce huge amounts of X-rays by sending electrons onto a target, onto some piece of metal, or bending the electrons. There are different ways, but you can generate X-rays. And also you can generate neutron beams, for example, sending particles against nuclei. So there are a lot of ways to use a particle beam, either directly sent on an object or indirectly to create secondary beams. Accelerators can concentrate a lot of energy, can deliver it very precisely. So it's a way to send energy on a very precise, very well-defined spot, And this is, for example, much more powerful than lasers, because also with lasers you can concentrate a lot of energy, but usually lasers are pulsed, so the energy is huge, but then you have a long time to wait until the next pulse comes, and lasers do not penetrate on the surface. And as you have seen from a previous speaker, there is what is the Bragg peak, which is a property of particles and only of particles, allows us to deliver the energy even beyond the surface, deeply inside an object. So really, in a sense, accelerators are magic tools to interact with the matter in different ways and also to be used in medicine. But how does an accelerator work? What is the trick? How can we make an accelerator? And now we are going to build together a particle accelerator. So what do we need, first of all? Well, first of all, we need the particles. And where can we get these particles? It's easy. The particles are inside the atoms. We have, of course, to extract them. And the trick, the way is very simple. We have to heat the atoms to give energies to the electrons and to the protons to separate. The simplest atoms that we can use to generate protons, for example, are hydrogen atoms. Hydrogen, one proton, one electron. And if you heat a hydrogen gas, you create a plasma of protons and electrons, and then applying a voltage, an electric field, you can extract your protons and repel the electrons. So it's a good way to create a proton beam. With an electron beam, it's even easier because you have to heat a filament. It's like a bulb that you have in your at home. Our a bit out of fashion electric bulbs, but in the old bulbs you have a filament that creates some electrons, and if you accelerate these electrons with a constant voltage with an electric field, you can create an electron beam. So this is relatively easy, and the good point is that there are a lot of atoms and protons around. So this that you see in this picture is the place where all protons of CERN are coming out, which is one single bottle of industrial hydrogen, which is the blue bottle that you see here. This is this. Here you have the inside you have 5 kilograms of hydrogen that contains. Look here, I don't want to read this number, just read it on the slide. How many billions of protons are inside this bottle? This is the magic of the Avogadro number for those that are familiar with chemistry. And this is really huge. And at CERN, you need only, I made a calculation some time ago, 1.2 millions of billions of protons per day. So, and actually I think that this battle will change every 2 or 3 months. It's the end of the, and you see, so this is where you can get your particles. But then what do you do? How can you give energy to these particles? The key of the process is what is called the Lorentz force. So if you have an electric charge, so a charged particle, electrons, protons, or ions, you can apply an electric field, and this will create a force that will move the protons or the electrons. And at the same time, if you have a magnetic field, we create a force that will deflect the particles. So you see here, a proton is positive, so it is attracted by everything which is negative, and it is repelled by everything which is positive. And if you take 2 tubes, like this one with a hole in the middle, and you have your protons, for example, going through, if the 2 tubes are connected, okay, here you have a battery, but to any type of voltage, you will have positive charges on one side, negative on the other, and your protons will be accelerated on this gap. So wonderful. So we have the particles, we have the acceleration. What we need more? We need the bending, because sometimes we have to control the trajectory of these particles. And this is why we can create a magnetic field, and this will deflect the particles. The particles will be deflected. So we can accelerate with an electric field. And the first thing that you would like to do is to create a very strong electric field to give the maximum possible acceleration. And so to increase the voltage from this battery. And this you can do, I mean, so here you have a picture of the old CERN pre-accelerator that had a voltage of about 800 kilovolts. So, but look here, what a huge installation you need for electrostatic acceleration at 800 kilovolts. So these are the two gentlemen here in this room. The ion source is somewhere here. Can you imagine? This is a Cockcroft-Walton accelerator. And in this room, all the walls are covered with stainless steel. So this installation we have dismounted. It was really very old in 1992. But I remember that when it was running, there was a spark. So the high voltage was sparking. There was a flash twice per day on average. And when there was a spark, you had a huge bang. So it was like the walls were trembling just for the forces when you have a discharge, electric discharge. So you can do it, but there is a limit to this electrostatic acceleration, which is electric discharge. To go to higher energies, you need something more. You need another trick. But before talking about this other trick, I will tell you why there was this, at a certain moment in the 20s, there was a race really to increase the energy of accelerators. Because the first experiment that was done by Rutherford in 1919 showed that one could change nuclei from one element to the other. It was the start of nuclear physics, was a new era for science, and people wanted to do it with more and more atoms. Changing in the nuclei was really a new page in the history of science, and there was a big request for accelerators of higher and higher energy, and the limitation was given by electrostatics. So you cannot really go beyond a certain, let's say, a few megavolts. Let's say is really the maximum that you can do with static machines. You have to go to another trick, and the solution was using oscillating fields, which is what changed the situation. And actually, this invention, the introduction of using alternate fields, was done by a PhD student, Rolf Wiederow, in 1928. So it was a huge, very interesting fact that a big step in the progress of accelerators came out of a thesis, a PhD thesis. So I assume that there are many PhD students that are now listening at this lecture. So you see, so now it's a little bit more difficult in 28. And it was easier, I think, for a student to make a great contribution to science. But nevertheless, I mean, keep in mind that PhD thesis can sometimes be very successful. And in this case, the idea was to connect a variable voltage to our tubes. Basically, you change the voltage between one and the other, and in this way, you can accelerate groups of protons. One more comment: how can you create this variable field? Wiederow, the great idea of Wiederow was to connect basically a radio generator, a radio transmitter. In the 20s, this was the start of the radio. So and he was a radio amateur, and he had a generator from a radio station, and he connected this to the tubes, and he has invented the first radio frequency particle accelerator. So how does it work? The point is that for example, like the protons, you don't have a continuous flow of protons. This is the first thing that you have to understand. The protons come in bunches, in groups of protons. And the protons go along so this is the hole between the tubes, and these are the tubes. So the protons are here, they find an accelerating field. But then, in this moment, the next tube, the next space between tubes has a decelerating field. But during the time they go from one gap to the other, the sign of the field will change, and they will be accelerated. So on and so forth. Next tube, there will be again next gap between tubes will be again accelerated, and again and again. So in this way, if you can create a few hundred kilovolts of acceleration between the tubes, the acceleration adds up, and you can reach 100, several hundred kilovolts, megavolts, gigavolts. You can add up acceleration. This is the basic trick of radio frequency acceleration. There are 2 points to be remembered: that the beam cannot be continuous, so you always talk about bunches of particles. It's always in bunches. And second, that there is a magic length that depends on the velocity of the particles. So the distance between gaps and also the length of the tubes must be very precisely defined so that this synchronism is kept. So that you have this synchronism from condition that the particles will always find accelerating fields. And all, let's say, the magic or the difficulty of particle accelerators is always to build larger and larger accelerators that always have to respect this synchronism between the waves, because variable fields come in waves, between the waves and the particle. And this is simply from Wikipedia. So it's a nice image of how all this work. So you go to linear accelerator on Wikipedia, and you see basically a Videro type system with a generator. Use the radio generator because it was accelerating at a few megahertz of frequency, and given a certain frequency and given the certain velocity of the particles, you know what is the distance between the gaps, and you see that the tubes are getting longer and longer because the particles are getting faster and faster. But the time for one particle to go from one gap to the other must be constant. So if the velocity increases, to keep the time constant, we have to increase the length. And so the tubes become longer and longer. Great. So now we have everything in our pocket to build an accelerator. And we've built a linear accelerator. And this is how it looks like. This is the real one, a linear accelerator. It is called drift tube LINAC. And this is now in operation here at CERN. You see the tubes, the hole, the particles go along this direction inside the tubes, and the particles, and what you don't see is that actually the tubes are longer and longer. But believe me, here inside the structure, the tubes become longer and longer to follow the increase of velocity of the particles. Okay, is it all? Actually not. There is another, let's say, problem that we have to solve. So we have learned how to accelerate the particles, but now we have to learn how to keep them together. Because when we talk of, you've seen how many protons there are in the bottle of hydrogen. We want to accelerate as many protons as possible to have more energy inside, and more energy density inside our beam. But unfortunately, particles of the same sign have the tendency to repel each other. So if we want to create a beam of protons of 10 to the power of 10, 10 to the power of 14 particles in a few square millimeters, the size of a bunch of particles is 1-2 millimeters. So it's not zero, but there is a certain dimension. But if you calculate, I mean, if you do nothing, these particles will start to go in every direction, and you will basically lose your beam. So what can you do to do that? You have to apply some focusing. And another important trick, another important feature of accelerators, that they always must have an accelerating system and a focusing system. Focusing, which is done using magnets, because we have seen that magnetic forces can bend your beam, and what you do, you let your beam go through a number of quadruples. This is a photo of a quadruple, and here you see the quadruple electric field. What does a quadruple do to a particle beam? Basically, it focuses in one plane and defocuses in the other plane. So if you alternate focusing and defocusing quadrupoles, the beam will be defocused, then focused, then defocused, then focused. So it will basically brief in the two directions, will change shape, but will remain confined. So it is a focused system. You can look at quadrupoles using the analogy with lenses. You have many ways to study this process, but the key point is that you using magnetic fields, using magnets, you can control the beam, you can transport your particles without losing them, and you can compensate for the repulsion between particles of the same sign. Examples of focusing, you see quadrupoles of different type. You can also use very small permanent magnet quadrupoles. What in a LINAC, you have a nice way to do it because you can hide your quadrupoles inside the tubes, inside the drift tubes. This is why they are so large in diameter, these tubes. In this way, you have created a system which is at the same time accelerating and focusing, which is what you have seen before, this drift tube LINAC. Great. So now we have learned how to build a LINAC, but is it all? Can we use a LINAC accelerator to go to very high energy? Well, let's make a quick calculation. With tubes, we can make about 2 MeV, mega electron volts of energy gain per meter. So we calculate the energy gain in electron volts, which is the energy gained by a proton or by an electron going through a voltage of 1 volt. If we adapt this, we can come to 2 mega electron volts per meter, which is about the accelerating gradient in a LINAC. And we cannot go higher because, as you have seen before, we will have discharge. We have sparks between the tubes if we go higher. So the Large Hadron Collider at CERN brings protons to an energy of 7 GeV, 7 giga electron volts. So if we want to build a linear Large Hadron Collider, it will belong 3,500 kilometers. So, which is, I mean, a bit long and might become expensive to build a LINAC of more than 3,000 kilometers length. The trick to pay less and to go to higher energy is the bending. So we need to bend the particles in a magnetic field. And the first who tried to bend particles was a gentleman, Ernest Lorentz, who has invented the first circular accelerator, which is the Cyclone. He had an idea, so instead of using tubes like we have seen before, he took half disks. This is like a tube, and you have a voltage with a variable frequency generator, a time variable generator, high frequency generator between the two half circles, the two disks, and in between you have the beam. And all this is closed inside a big magnet, so that you have a vertical magnetic field that will force the particles to go in circles around. The ion source is in the middle, which is the important point. Here the particles are created with very low energy, so they receive a first acceleration between the two plates, then they go in circle, a second acceleration, and every time they receive more energy and they go into larger and larger circles. They go into larger circles because of the magnetic field that is given by the Lorentz force that we have seen before. And there is the cyclotrons work thanks, let's say, to a fortunate coincidence, something that really works very well. The fact that if you calculate the frequency of revolution to go one turn, it's you see that it depends only on the mass of the particle on the charge of the particle and on the magnetic field, which is fixed. So the frequency, so the particles remains always synchronous with the accelerating field. The synchronicity condition that we have seen before between tubes is respected here, but the tubes are not longer and longer with the velocity of the part. They don't get longer and longer, but here what gets longer and longer is the circular path inside this cyclotron. So cyclotrons are very good accelerators, very compact, can go to very high intensities, can accelerate many particles, but and you see how they look like. So here you have examples of cyclotrons. So you see the big magnet, and the accelerating gap is in between. So you see, you can go to higher and higher energies. This one is for 70 MeV protons, larger and larger. You see even a vertical cyclotron like this one, but you cannot go to higher energies. It is very difficult, or let's say it is very difficult to go beyond, say, a few hundred of MeV of energy. Why? Because we have to fight against another problem. Or we have to fight, okay, we don't fight against him, but actually we have to find a way to solve a problem that comes from Mr. Einstein. So Einstein is not a problem, simply he shows something which is very interesting, and it's an additional problem or challenge for particle accelerators. The fact that if you give energy to a particle, first of all, when you are in the realm, in the domain of classic mechanics, the energy goes to increasing the velocity of the particle. The velocity is increased, but at a certain moment, you see here, I plotted v over c, so velocity over speed of light square of the particles, as a function of energy for a proton, for one proton. If it would be in the classic mechanics forever, the velocity will increase forever and will become higher than the speed of light, which is not possible. Speed of light, you know, is a limit that cannot be crossed. So what happens is that when you keep giving energy to the particles, at a certain moment, it is not the velocity that is increased, it's the mass. If the mass that is increased, the particle becomes heavier and heavier. The energy is still higher and higher of the particle, but the velocity increases very slowly, and at the end you approach the speed of light, and only at very, very high energies you almost reach the speed of light. Out of the Large Hadron Collider of CERN, the velocity of the protons is 99.999 and something like that % of the speed of light, but it is not the speed of light. We'll never, never, ever reach the speed of light. And this means that all our trick of the tubes getting longer becomes very complicated if you go to high energies. If you start going for protons around of the order of hundreds of megaelectron volts, because the tubes, the length of the tubes become constant, which is good for an accelerator, but anyhow you don't use it because it is too expensive for high energies. But for example, it's a problem for the cyclotron. The cyclotron, you can no longer respect this rule of constant revolution time, which is the reason why cyclotrons work. You can change that, you can correct that, going, for example, to synchrocyclotrons. You have special designs that allow to go a bit farther in energy, a bit higher energy, but it is not enough. Cyclotrons at a certain moment are limited in energy. So you need something different. And what we do is the synchrotron. The synchrotron is a larger accelerator where we have, on a circular path, we have 3 types of elements in a synchrotron. We want to keep the particles on a circular trajectory, and we need bending magnets. We need magnets, you see them here, where you have a vertical magnetic field, and they keep the particle on a circular path. Then between one bending magnet and the other, the particles go straight, and they go through two other types of elements. Accelerating cavities, and here you have the cavities, basically one or more gaps, as those that you have seen before, where the particles get acceleration. And then the third element of the synchrotron are the focusing magnets. Quadruples, usually, as you've seen before, and they keep the particles on a closed trajectory. So on a synchrotron, you have, the synchrotron can be bigger and bigger, and the largest synchrotron in the world is the Large Hadron Collider, which is 27 kilometers in circumference. And synchrotrons, but all synchrotrons are very similar. They are all based on three basic elements: bending magnets, accelerating cavities, and focusing magnets. How can they work? What is the trick to make a synchrotron work? The idea is that you use, if you calculate the time of revolution of the particles, if the particles are relativistic, so if they are closer to the speed of light, their velocity is constant, is the speed of light, and the time for a revolution is constant. So no problem, you are always synchronous with your accelerating fields, RF fields, and the synchrotron works. Instead, you have to change during the acceleration, because the mass of the particle increases, you have to change the magnetic field. And all the trick is that in a synchrotron, we increase the magnetic field to keep the particles on always on the same orbit, on a fixed orbit inside the synchrotron. Synchrotron, you see, this is why usually you need a linear accelerator as an injector to a synchrotron to go through the Newton part, the classic mechanical part of the velocity of the particles, and the synchrotron is covering the part where the energies where the particle is relativistic. In between, you can have some tricks, because there are also ways to start the acceleration in a synchrotron, even if the particle is not fully relativistic, because within certain margins, you can change the frequency of your accelerating cavity. So this is why you also use synchrotrons. And this is a nice scheme to show the difference between a linear accelerator and the synchrotron. The linear accelerator, you have different gaps along a line, and they are longer. The distance is increasing to follow the increasing velocity of the particles. In a synchrotron, basically, you have only one gap, and you have a closed circle. Here, you have only one accelerating system. You see, this is much less expensive. It's cheaper to build because you have only one accelerating gap. But you have to build this circular path that requires a number of magnets. And at the beginning, to keep the synchronicity, when the velocity is still increasing, you slightly change the frequency of this in this synchrotron proportionally to the beta c, which is the velocity of the particles. So variable distance and constant distance, but variable frequency. While here you have variable distance and constant frequency. In this way, you can easily build a synchrotron. And this is an example of a synchrotron, the one from the CNAO used for ion therapy. And you see that you see the main parts of a synchrotron, which are the injector linac, which is here. You see, inside the synchrotron, you see the main components, the bending magnets, the quadrupole magnets, and somewhere there is not very visible, you have the accelerating cavities. And our particles are kept on a circular trajectory by varying the field in the magnets in order to keep them on a constant circle, which is this one. The magnets, you see them here. A dipole is here. This is a conventional dipole. There is a winding. There are two windings, an iron here and the magnetic field. Basically, these are two solenoids with the magnetic field that goes inside the solenoids. You have the iron that is meant to increase the field, and the particles go between the two parts of the magnet. What I have to tell you is that there is another interesting way to build magnets at higher field, because you see the limit to the, if you want to go to higher and higher energies, you need larger and larger synchrotrons, or you need more magnetic field. And the only way to keep the synchrotron dimensions relatively smaller is to go to superconducting magnets and the superconductivity. So the difference is that here you can have 1 to Tesla of field, talking Teslas, while in the magnets of LHC, for example, we reach 8 Teslas, and now there are projects to go to 10, 12, even 16 Teslas for the magnet. Superconductivity is the key to keeping dimensions smaller. I'm approaching the end of my first lecture. This is just a scheme of the CERN chain of accelerators to show that because we are limited by the field in the magnets and by the dimensions of the synchrotron, if you want to reach higher and higher energies, the only solution is to go from one small accelerator to a larger one, to go in steps with the acceleration to larger and larger accelerators. This is why at CERN we start from some linacs, we go to a small ring, then to a second larger synchrotron, to a larger synchrotron, and only after all this complex process, protons have enough energy to go to the large hadron collider, where and only when their energy is, their velocity is practically equal to the speed of light. So this is the reason why only at this moment we can go to the Large Hadron Collider. So superconductivity, as we will see also in the next lecture, is the key to the future of particle accelerators, one of the keys. Superconductivity, because we can build magnets that do not dissipate energy and can go to higher and higher field for this reason. But we can also build accelerating cavities made in niobium that are superconducting, that allow to reach higher and higher fields without losing too much power. But we have to keep everything cold to 4.5 K in the LHC, and here you see the huge refrigerating system of the CERN Large Hadron Collider. So superconductivity, so during the history of particle accelerators, there have been many improvements. Superconductivity is only the last one, but still, I mean, now we are looking at what are the possible steps in the future of particle accelerators, what are going to be the next technologies that will allow particle accelerators to be more and more powerful and to concentrate more and more energy in the particle beam. This is still under study. What I wanted to mention to you just only is the work that goes into what we call the miniature accelerator, because on the one hand, physics, for particle physics, now the request, the demand is to build larger and larger accelerators that can reach higher and higher energies. But in many applications, like for medicine, instead, the request, the demand is make it small. Make small accelerators, not very high in energy, but smaller and smaller, so that they can be less expensive, they can be installed into hospitals, and this is a way to make the particle accelerator technology more accessible to medicine and to industry. And there are several examples. Here I wanted just to mention 3. So we had done some work on the construction of a miniaturized radio frequency quadrupole. You see here how small is this small linear accelerator. This is also used for medicine. You will have an example in the next lecture, but also for analysis of artwork. And we have one which is in construction now for producing particle beams to inspect the chemical composition of paintings and artwork. We have systems based on X-band technology, 12 gigahertz, very high frequency, that can be used also in medicine, but also for for many industrial applications. And then you will see in the next lecture, we will speak about magnets for very compact synchrotrons for ion therapy. So I thank you here for your attention, and this is the end of my first lecture. I will stop sharing, and unfortunately, I don't hear any noise. I think that I have probably to, if you give me 2 minutes of
questions.
2 minutes, I will try to see if I can restart my my audio. So if somebody, Jota, can you do some, can you so,
Κάνε μεγαλύτερο.
can you make some zoom? Yes, okay. Questions. All right. So I will try to, I still have the problems with my audio, so I will try to read the questions, and then I will answer them. Okay. So Jota, make a sign if it is okay for you.
Yes, yes.
I don't see you.
Yes, yes. Yes, Maurizio. Yes.
Okay, good. Okay, so for this question on the ion therapy gantry, please leave to the next
Yes.
yes. Lecture. How often does the 5 kilogram cylinder of hydrogen get changed in a clinical center? Okay, in a clinical center, it is not 5 kilograms, probably it's less, and probably it lasts for a year or so, something like that, I think. But you don't wait until it gets to the end. It's like in your car. You don't wait that you run out of gasoline to refuel. Hydrogen is very small, so you really you change it very often, more often than you really need. Yes. So great presentation. Can we use cyclotron to accelerate electrons? And if yes, can we use them to create photons for treatment? No, we cannot use cyclotrons to accelerate electrons. Why? Because electrons are much lighter and they become immediately relativistic. So you give them a kick and immediately they are relativistic. And you cannot use a cyclotron with a relativistic particle. So cyclotrons you can use only for protons and for some heavy ions. Yes. What you can use, you can accelerate electrons, for example, if you want, with this, what you have seen in my last slide, there was this X-band system. This is an electron accelerator, and this can be used, for example, to create photons. So there are different ways to create protons, more modern than what you will see in my next lecture. For what all do we use a synchrotron accelerator at CERN? I don't understand this question, but I think that this refers to the fact that at CERN we use synchrotrons for experiments of particle physics, so to make collisions, head-on collisions of protons to create new particles, to generate, sorry, not to create new particles. And this is why we use synchrotrons at CERN. As far as I know, there is a limit of how big magnetic field you can induce. Does then, yes, question number 5 is very correct. And this I also said at the end, but maybe I was too fast, that in magnets there is a limit to the field that you can reach. And if you want to increase the energy, you have to go to a larger synchrotron because you bend less, so you can go to higher energies with the same magnetic field. And this is the problem now, is that, for example, at CERN, we want to build a new accelerator for higher energy, and we cannot really increase much the magnetic field, and the plans are for a 100-kilometer ring instead of 27. So this because there is a limit to the magnetic field. Is there a new breakthrough that could change technical limitations of accelerators? People is working a lot, for example, on accelerator in plasmas using lasers, in coupling lasers with plasmas to go to, instead of using accelerating radio frequency and gaps, because in a plasma you can stand very high magnetic fields, a lot of megavolt per meter. So it's not yet a breakthrough because there is still a lot of work to be done, but there is people exploring new directions to change the technical limitations of accelerators. It's not for tomorrow, but there are really hopes that there are other systems and there is really work now in going to beyond the limitation of accelerator, also because this technology you have seen these people inventing radio frequency accelerator in 1928. It's almost a century ago. So it's, in a sense, it's an old technology, very mature, but old. There is people working on new directions for accelerators. Would a miniature accelerator be effective to accelerate the particles? Yes, it is. So actually, miniature, I mean, you don't, not really centimeters, but we are talking of meters of length. Meter. So the point is not so much the size, but the point is to have as many megavolt of accelerator in a small volume. Is how much you can, how you can reach the highest possible acceleration in the smallest possible volume. How did Mavion make such a small accelerator? What is the drawback compared to synchrotron system? Now, Mavion, it's a small accelerator, is a superconducting cyclotron, but it does not reach at high energy. So the energy is still relatively low, what is needed for proton therapy that we will see in the next slides, in the next lecture. So what we want systems that, and it's always comparing synchrotrons with cyclotrons is always difficult, but in general, at low energies, cyclotrons are better. At high energy, synchrotrons are better. In between, there can be some discussion. Okay, we can discuss. What is the smallest size of proton accelerator for cancer therapy? You will see in the next lecture. It is still a design, but you will see this in the next lecture. Why are we continuously focusing and defocusing particle beam when we only want to focus them? Good question. It is, unfortunately, you cannot only focus with a magnet. You cannot invent a fully focusing magnet. So actually, this is Murphy's laws. You can't win. So you can always, if you focus in one plane, so in X, you will defocus in Y. And we cannot make a magnet that focuses in both X and Y, in both planes. So the system of focusing and defocusing is used to defocus in one plane and focus in another, and to reach a stable configuration thanks to that. So actually, you defocus little because you put the defocusing magnet when the beam is small, and you put the focusing one when the beam is larger, when it goes more towards the end of your magnet, when the field is stronger. So this is basically a trick. But if you make the calculations, you will see that your beam is stable thanks to this trick. Okay, so we have all the, okay. I go to the second lecture. Jota say yes, okay. Sorry for the trouble. Just wait a moment that I have to prepare my screen. This is the second lecture. Yes. No, it is not this one. Where is it? Yes, this one. Yes. Now I have it. Yes. Okay. Jota say yes. It's okay. Okay. So let's go for the second lecture. What's the time? 54. All right. This one is more specific on accelerators for medicine. But before going to accelerators for medicine, I want to say a few words on accelerators for society. Because when we think of accelerators, we all have in mind the large machines at CERN, the big accelerators. But this is only the top of the iceberg. Nowadays, there are in the world more than 30,000 particle accelerators, and only a small minority are used for research. And only a small minority, less than 1%, are used for particle physics. Yes, of course, these are the largest accelerators, the most visible, but this is just a minority. 6% of accelerators all around the world operate for research, and the rest is well shared between medical applications, about 1/3 of all accelerators in the world, and industrial applications, a bit more than 50% of all particle accelerators in the world. In medicine, we will see how they are used, but in industry, what I can already tell you is that in industry, they are used, for example, for ion implantation, many of the semiconductors that you are using in our electronic system are made by doping semiconductors using ion beams produced by an accelerator. It's something that you also many don't know, is that the plastic film that you use to wrap food, for example, at home, very often the chemical bonds are making stronger and more flexible thanks to a treatment with an electron beam. This is treated with a particle accelerator. So the fact that you can concentrate with the accelerator huge amounts of energy into a tiny volume is useful in energy, but also in medicine. And here I will go through a review of the different uses in medicine. And for this, I have made this nice cartoon that shows how accelerators can be used in medicine to interact with the human body. Here we are not thinking about smashing particles against others. We are seeing how we can use them on the human body. And there are different ways. So of course, the easiest is to send directly your beam onto a person. See, here I selected a strong guy just to stand this beam. And you can send 3 types of beams. What you can accelerate? You can send protons, ions, and electrons. If you send protons onto a patient, then we are speaking of proton therapy. Ions, ion therapy, and the 2 are called hadron therapy because protons and ions are hadrons. Then you have electrons. You can send electrons on a patient at low energy or at high energy. We will see the different properties of IORT and VHEE. But you can also send something different onto a patient, because we have seen in my first lecture that accelerators can be used to produce secondary beams. So if you send the beam onto a target is just a block of metal, of a particular metal, where the energy of the particles is converted, for example, into X-rays. And X-rays can be produced by electrons sent on a metal target, are used for radiation therapy. And we have around the world about 14,000 radiation therapy systems. It is the most widespread particle accelerator. We can use also neutrons. There are some applications of neutrons produced with accelerators, but there is another nice way of using accelerators in a 2-step process. First of all, on the target, you produce radioisotopes with the accelerator. And then you carry the radioisotopes in a shielded box to the patient. And these radioisotopes are injected into the patient for 2 applications: imaging and therapy. You can use them, the radioisotopes, to make nice images of the body, of what happens inside the body, and you can use them for therapy. All these applications share one, let's say, one image, a vision, which is the vision of using accelerators for bloodless surgery and imaging. It's always been an old dream of humankind to be able to see inside the body and to treat, to cure a body without opening it up, without blood. And thanks to particle accelerators, we can now fulfill this vision, and we have an opportunity to penetrate inside the body, to see it thanks to the imaging with the isotopes, and to do treatment thanks to X-rays and thanks to protons and hadrons that will allow us to do. And this is all the basis of nuclear medicine, which is a growing field of medicine. It all started, this was showed already by Manjit Dosani this morning, by the ideas of Ernest Lorentz, the inventor of the cyclotron. Lorentz, a lucky coincidence also for using accelerators for medicine, is that Lorentz's brother, John Lorentz, was a medical doctor, And together, they made a lot of experiments at the first cyclotron or medical applications of cyclotrons. And then you also was mentioned this morning that this was then there was the first application of the bragg peak of protons to cure cancer, what came from was in the 40s by Bob Wilson, and then the first treatments in hospital are dating only from the early 90s. Only 30 years that patients are treated in hospitals, but before they were treated outside of hospitals. And here I want to draw your attention on a few important points that we have to remember when we consider accelerators for medicine. The first is that for science, we can play. Science is a game in a sense, and you can always, it's very experimental, but medicine is not a game. We cannot play. So it is very serious, and we have to be absolutely sure that the quality of the condition of our beam are perfect, not to harm the patient in any way. Everything is must be very well controlled and very well under controlled, and the quality of our beam must be of the top quality to be used for medicine, different from what is the case for science. And to give an idea, it's very simple. We have a colleague who builds control systems for accelerators, and he told me, for me it's very easy. I mean, factor 4. So there is a factor 4 in the cost of a control system for a scientific accelerator and for a medical accelerator. So because you need all the different control levels, you need different levels of control, you need the different safety requirements, and all this adds up to the complexity. So this is something that we have to remember, is that accelerators for medicine are very special for this reason. And you see how far one can go between the first treatment, this is Lorentz's brother, John, at the first cyclotron, the first treatment of a patient that they did in the 30s on a scientific cyclotron, and nowadays a model treatment room. So this is something which is very important. Those are two different words. And the second point that we have to keep in mind before entering into the discussion on medical accelerators is the fact that all the trick is managing radiation dose. Because on the one hand, you need a strong dose for your patient. So you're going to kill the tumor, sparing the patient, and there is a window of effectiveness that you have to center, where you have to, so if you give it too low a dose, it is not effective. If you give too high a dose, there is a risk of damaging the patient. The window is very narrow, so this is why you want to control very, very precisely your beam and the dose that you're going to deliver. Usually it is a strong dose, and around this patient, there will be doctors, there will be technical people, and the point is that the limits for the dose that they can receive during their work is very, very low. Here, for example, the limit doses for CERN workers, and these are very low. I mean, these people in the hospitals, they spend all their working day next to sources of radiation. And so, of course, the overall dose that they have to take is very low. So this is why there is another, not one problem of medical accelerators is that you need to control them very carefully. And the second is that you have to control the radiation protection, let's say, is a very important issue in medical accelerators. Radiation protection of the patient from excessive dose, but also of all people working on medical accelerators. So there is a lot of work to be done, and this is a key issue for developing medical accelerators. But let's go now to look a bit more in detail to different types of accelerators, and I will go quickly through a review of the different applications of accelerators for medicine. And so I will start from accelerators of electrons for radiotherapy. So this is the most successful accelerator that we have ever built. The beam of electrons is accelerated by a small accelerator, is 1 or 2 meters. It's really very short. Electrons are immediately relativistic. So the drift tubes, if you remember my previous lecture, are all of the same length inside the structure. And you can see them here, for example, or here. and then the beam is bent and sent into a tungsten target where the X-rays are created. The modern radiotherapy is very precise. I don't want to go into too many details, but you can, first of all, to reduce the dose, because electrons, X-rays, pardon, don't have the break peak. So you burn the skin, and really you can create, you give a certain dose to the tissues that you have to cross before reaching the cancer. So solution number one is to give the dose from different angles. And you see here an example of a cancer which is treated from different angles. And the dose, the maximum dose is here in the center. And then what is done in modern radiotherapy is to create contours, to make collimators, tungsten collimators that simulate the shape of the tumor to send the beam exactly on a certain size. So it's a sophisticated way of treatment, which is also not very expensive compared to other methods of treatment, but you don't have the benefits of the break peak. Instead, if we go to hadron therapy, then we really have the break peak. It was mentioned already before. All this comes from this long equation that I don't want to discuss. It's the Bethe-Bloch equation that tells you how a particle loses energy inside any kind of material, which can be a metal, air, or even can be the human body. And you see that compared to X-rays that lose energy very progressively, particles at the beginning, they lose very little energy, and then they lose a lot. This is a kind of resonance, because the energy is lost by interaction with the electrons of the atoms. So at the beginning, the particles are too fast, are very fast. They don't have the time to interact with the atom, and they lose energy very, very slowly. But at a certain moment, when there's a kind of a resonance, because the time that they need to cross the atom is enough to maximize the transfer of energy to the electrons. And here you have the break peak, and you transfer the energy to the electrons. You excite the atoms, and you break the molecules. And at a certain moment, the energy is too low. You cannot penetrate. The particles are repelled by the electrons. They cannot penetrate the atom. And then you have a sharp decrease of the energy, and all the energy is deposited. And this property, this resonance, is what can be exploited by hadron therapy. This you will have many lectures this week, so I don't want to give into many details on comparing what is the therapy using the break peak or using standard X-rays. I only want to comment that there's been a big increase in the uses of particle therapy in recent years, but there is much less growth, say, around the world with ion therapy because of the cost and the dimensions of ion therapy accelerators. Despite the fact that ions are more effective than protons or X-rays, because they lose more energy, ions, because they are more charged, simply because of that. Ions are, a carbon ion has a positive charge of 12 electron charges, so they interact much more, and so they lose energy more quickly, and they give a lot of energy to the molecules they cross, so that they break the DNA. They break the DNA in different positions, and they create double-strand breakings that most often are not repairable. So if you have a single-strand breaking of DNA, our cells are so clever that they can repair it. But if you break twice the same DNA, then the molecule gets crazy, and the molecule cannot repair the DNA. So the mechanism of action of ions is completely different from protons or X-rays that interact with the equilibrium of oxygen within the cells. So carbons have a different mechanism, which makes that they are effective also with hypoxic tumors, tumors that are radioresistant. They can be combined with immunotherapy, and there are some interesting, there is an interesting work in progress on the benefits of ions for that, combined with immunotherapy, but they are less used. Why? And now I come to the question, why the gantry for ions is so big? You see here an image of the gantry for ions of Heidelberg, simply because the benefit of ions comes from the fact that they lose more energy inside the body. But the drawback of the fact that they lose more energy is that they need more energy to penetrate fully inside the body. So with protons, we need only 250 MeV to penetrate through, I think, 30 centimeters of water, or let's say inside the patient. With ions, for example, carbon ions, to enter into the same depth, to make the same trajectories, to go to the same target tumor, you have to start with a much higher energy, 440 MeV per unit, per charge unit, because the energy loss is higher and you want to reach the same position inside the body. So nothing to do. This is so if you want the benefits of the ions, you have to pay with the fact that you need a higher energy. And this higher energy means that the accelerator is bigger. In particular, as we have seen, for a given magnetic field, the radius of the, or let's say, there is a law which relates, which is relativistic, basically, it comes from relativity, that relates the energy of the particles with the product between the radius of the accelerator, of the synchrotron, of the accelerator, it's valid also for the cyclotron, and the magnetic field. For the given magnetic field, so B, the difference in energy between protons and ions is such that you need about 2.8 times higher radius with ions than with protons. So if you do nothing, you just scale a synchrotron. A synchrotron from for ions is 2 times bigger than a synchrotron for protons, and a gantry for ions is 2.8 times bigger than a gantry from protons. And you see this guy here, it's 2.8 times bigger on what would be an equivalent gantry for protons. You will see in the last part of my lecture that all the work that we are doing now to optimize and to improve ion therapy is to find ways to fight against this factor 2.8. So to build superconducting accelerators that are smaller, that are comparable in size and in cost to the proton accelerators, to beat this drawback of the factor 2.8 in magnetic rigidity, let's say, that comes from the higher energy. But is the price that we have to pay for the benefits of the ions, or for the higher energy loss per meter the ions inside the body. Proton therapy is easier in this sense because you don't have this factor, can be done by cyclotrons. It's still, 230, 250 MeV per MeV. It's an energy which is still reachable by cyclotrons. Cyclotrons are much smaller, but you can do it also with synchrotrons. And synchrotrons like CNAO and Heidelberg have been designed for dual use of protons and ions. Now we are going more and more in the direction of a divorce between the two types of therapy, because proton therapy you can do now with smaller superconducting cyclotrons that are more compact. And on the other hand, we are now going to try to see if we can improve the technology for ion therapy, doing machines that are really optimized for ion. So combined on the old machines, and now we are really trying, we are going slowly towards a divorce between the two types of acceleration. I have also to mention another option, because it will come again in the rest of the lecture, which is using linear accelerators. So before in the first lecture, I told you that it is crazy to go to high energies with a LINAC because it will be very, very long. On the other hand, for medium energies, like the one that you need for proton therapy and also for carbon ion therapy, you can think of a LINAC if you make a linear accelerator with a high gradient, with a large number of megavolt per meter. You remember in my previous example, I was talking of 2 megavolt per meter, and here we are thinking at 50 megavolt per meter in a linear accelerator. Using special technologies, very high frequencies, there are some developments, and at the moment there is one proton therapy LINAC, which is actually in construction. Since many years in the UK, is in construction a proton therapy LINAC, and there is also people working a design of a linear accelerator at high frequency for ion therapy. The advantage of a LINAC is that it is, while there is always the distance between bunches of particles. I told you that accelerators are always in bunches. In a synchrotron, you have a certain number of bunches, and then you have to ramp the magnets up and down, so you have a big hole between different trains of bunches. In a LINAC, you can pulse them very at a high repetition frequency. You can have many bunches in a LINAC, and you can change the energy very easily to scan the tumor longitudinally. You can do it also with synchrotrons, but it is more complex. So this an advantage of the LINACs is that it is easier to scan. They have a smaller emittance, no beam loss, but nobody has ever used a LINAC so far, and there is a complete system of quality assurance, beam control, beam stability. There are all questions that are still to be addressed. I told you that the beam has to be known very precisely, but if it is pulsed very rapidly, it is very difficult to know precisely every pulse, the beam properties for every pulse. So there is still some way to go before using LINACs for therapy, but there is work in this direction. Okay, I go quickly to the other applications of accelerators. Electrons can be used in two ways. Already now, there is people treating directly tumors with electrons with interoperational radiation therapy, which is the way to irradiate with electrons directly at tumors, the area around the tumor after the operation. So you take out, after removal of a tumor, you can treat against malignancy the region around the tumor directly with electron beams. And there are experiments about using electrons at high energy. So this is still experimental about using on the side of the accelerator. Nobody has yet used it for treating patients, but there are also work on using electrons at high energy and combining them with flash therapy, as you have heard already this morning. Radioisotopes, so there is work on using radioisotopes. There is production of radioisotopes at accelerators, which is done usually in cyclotrons, dedicated cyclotrons to produce radioisotopes. Energies are relatively small, and the main isotope used is fluoride 18, produced accelerators for PET scanning. And this is there is a growing number of accelerators used for production of isotope scanning. And there are also other isotopes of interest we will see later on. And then I will finish my review of applications on the use of radioisotopes also for therapy. So there are different techniques that are now in advanced trial phase of treating tumors by injecting the isotopes that are connected to antibodies that can stick, for example, to a tumor cell, and the radioisotope release its radiation on the tumor. So it's very difficult to control the dose, but it is very effective because, for example, emitter of alpha particles, helium nuclei, alpha particles are very damaging for the body, for the organism, for the cells, and if we can really stick alpha emitters on a tumor, we have found a great way to cure not only solid tumors, but also diffuse tumors and metastases. And this, from my point of view, is going to be an increasing application of accelerators in the future as soon as these clinical trials will come to the end to hopefully success. There will be a big demand for accelerators for treating, for producing radioisotopes for treatment of cancer. Okay, and one of the main isotopes that can be used for that is astatine, which is an unstable chemical element that can be produced by accelerators and can be used for targeted alpha therapy. Now let's use the last 15 minutes that we have to go a bit through the new technologies that we are at the moment studying for the next generation of accelerators. Why do we need a next generation of ion therapy? Because at the moment, the growth of ion therapy, despite its advantages, is limited by the size and the cost of accelerator, and on top of that also by the lack of experimental data, which is also a consequence of the fact that there are few ion therapy accelerators in the world. So really what the community, the scientific community, wants is a new generation of accelerators that are smaller, not such a big gantry as you've seen before, that are less expensive, possibly with much higher beam intensities for faster treatment of the patient, and equipped with a rotating gantry. This is a kind of a must for future accelerators. So this is why there have been several initiatives around the world on that. We are working at CERN since 2018 on what we call the Next Ion Medical Machine Study, which is developing a portfolio of technologies for next generation ion therapy accelerators. You have seen already this morning was mentioned this new initiative in Southeast Europe, the CEIST, the Southeast European International Institute for Sustainable Technologies, which is a partner of NIMS and also a kind of a reference user of the NIMS technologies. And inside this collaboration, we are now working in 4 directions. The first is developing a new generation of superconducting magnets. So the key to smaller and cheaper accelerator is superconductivity. There are no other directions. But, and we have a lot of experience at CERN and in other places on superconducting magnets. So there have been 2,500, I think, superconducting magnets built for DHC at CERN, but they are all almost straight at very high field because the bending, the curvature is very low. Here we need magnets with a strong curvature that are pulsed, they're not fixed field almost as in the case of DHC, and magnets that need to reach a high field level. So it's a complicated technology, and we really need to go one step in this direction for the next generation ion therapy accelerators. We also work at CERN on the option, on the LINAC option, trying to see on the carbon ion version of the LINAC accelerator. We also want to work on gantries, on a new generation of gantries that can be used for the next machines, but also as an add-on to old machines, existing machines like now or Medaustron. And then we want to work on synchrotron design because there is a lot to do, in particular for the higher intensity, to accumulate more particles, more beam into the synchrotron, and to make the synchrotron smaller if you want to use superconducting magnets. So this is why we have started some time ago, a year ago, comparing 3 options of accelerator. The first one is a normal conductor standard synchrotron with conventional room temperature magnets, about the size of Heidelberg and Knau, but with some new features to accumulate more beam. So there is a lot of work that was done at CERN and elsewhere in our collaboration for technologies to store more beam into this synchrotron. We are now also looking at a new design for a linear injector, and this is part of our, let's say, comparison, what would be a modern room temperature magnet synchrotron. But we want also to see how the synchrotron would look like if you make it superconducting. So the limit is a square ring. It's a square synchrotron with only 4 magnets, making 90 degrees superconducting at high field and small dimensions. Here you see that we have about 27 meters in circumference that you can reach with superconducting magnets, to be compared with about a factor of 3 higher circumference that you have with conventional magnets. This is because we want to reach a factor 3 higher field in the magnets thanks to superconductivity. And then also we have compared the small footprint of a linear accelerator, which is only 53 meters, but can be bent in 2 sides. We have compared the different options, and you see here 3 layouts based on conventional synchrotron, superconducting synchrotron, a linear accelerator. And at the end, our conclusion is that what we have advised seized is that as initial baseline design, it should be based on a room temperature, on a normal synchrotron, because there is still quite a lot of R&D to be done to reach, to be able to produce curved superconducting magnets for synchrotrons. But over the medium long term, this is the future. This is technology for the future. And so the design, so if CEIST has to build quickly an accelerator, it can be normal conducting. If instead there is more time to wait for the development of the magnets, it must be superconducting. On the other hand, and then the LINAC is another option that is more longer term because requires more R&D and also requires a change in the quality assurance protocols to cope with a particular way of functioning of a LINAC as compared to a synchrotron. However, the advantages of a superconducting synchrotron are not very evident in a facility like the CEIST that you see here has 2 experimental rooms, 3 treatment rooms, so it's a big facility. Instead, the advantages of a superconducting synchrotron would be very clear if we make a single room, very small facility, operating only with a synchrotron, as you see here, and a superconducting entry. In this way, you can keep the accelerator with all the shielding in about 1,000 square meters, which is comparable to existing proton therapy systems, and we really pave a new way for the application of ion therapy in every environment, including hospital environments. Recently, our colleague Elena Benedetto has developed a design for a triangularly shaped synchrotron that you can see here, and this is the kind of direction that we now want to explore over the next years of research. However, one of our main directions of exploration is in the field of superconducting magnets, and in particular new designs of magnets. There is quite some interest in using magnets of the so-called canted cosine theta type. I don't want to go into many details, but these are made with 2 windings with a slope. Each of them is a solenoid that produces a magnetic field with a certain angle. You see here 2 angles, but if you combine them, it gives the vertical magnetic field that you want in a superconducting magnets. Canted cosine theta magnets for new ion therapy are the subject of 2 European projects that have been recently approved. One is the project that is supporting this school where we are now, which is HITRIplus. HITRIplus is a strong work package of magnet design of this type, canted cosine theta, for ion therapy. And then there is another project which is called IFAST that also has a work package on industrial prototyping of future generation ion therapy magnets. All this for the benefit of the CEIST facility. Okay, but I told you already that there are foreseen 3 therapy rooms, only 1 equipped with a gantry, and 2 experimental rooms, and a LINAC, which is the injector to the synchrotron. Let me say a few words more on the LINAC injector, because it is also a very important element, important for the cost, for the reliability, for the beam quality of the synchrotron, but also because if you consider that a synchrotron is pulsed, because the magnets have to go up and down in field, most of the time, so the LINAC will fill the synchrotron and then wait for all the treatment time before filling again the synchrotron. And during this time, it does nothing. Our idea is that instead, the LINAC could be used during the interval between two injections into the synchrotron for the production of radioisotopes. The energy is about fine, it's very good for what you can get from the LINAC. So from the LINAC, you have one line going to the synchrotron and another going to a radioisotope production target where you could produce isotopes. And we have identified 3 types of promising isotopes that can be produced with a LINAC about the size that you need for this facility. One is astatine 211 that you have seen for targeted therapy of many types of tumors. Another is metastatic tin 117 for theranostic, HITRIplus, and bone malignancies. They are both produced with alpha particles that can be accelerated by the LINAC. Astatine is very interesting because it's created with alpha particles, and basically the astatine borrows the alpha particles that you produce with the LINAC. You inject it to the patient, and into the patient it releases the alpha particles that you have given to it. Just a carrier of alpha particles from an accelerator to a patient. And then there is also quite some interest in using LINAC for production of isotopes for PET scanning, but short life isotopes. The isotopes that now are in use have a long lifetime because they are meant to be transported by airplane, by lorry, from the cyclotron production to the hospital. If you produce the isotopes next to the treatment center, to the hospital, you can use isotopes that have a much shorter lifetime and much less dose to the patient, and also sometimes being also more precise. A few words now, I'm approaching the end of this second lecture on the gain tree. So the gain tree you have seen is an important element in any ion therapy facility. We don't want to make the big gain tree that you have seen before. You have seen that ion gain trees are larger than proton gain trees, but we have to use science to make them smaller. How we can do it? By building structures that make use of superconducting magnets. And here you have a few pictures that are taken from a note that was recently produced by a number of my colleagues that you see here. This is a version of a high field version of a gain tree that has a radius of only 5 meters radius. You see very, very small. You see here compared to the patient that makes use of CCT, canted cosine theta magnets, and rotates not for the all 360 degrees, for something less, because the gain tree is attached to a wall or to a pillar here in this position. However, canted cosine theta magnets require probably a few years for development. So the duration of these European projects is 4 years. So we just started. So we can hope only 4 years from now to have some prototypes of CCT magnets. This is why now it's been it's in progress the design of a version of gain tree that uses magnets of a more conventional cosine theta type, like those of LHC of the other accelerators, which is a bit bigger because the field is only 3 Tesla instead of 4, but still, I mean, it's less than 7 meters, the radius of this gain tree, and you see here how it can look like. And this is meant to be produced in about 10 years, and you see here the first design of the magnet. And now this is the end of my second lecture, and I want to show in what you have already seen the artist view or the conceptual layout of the CIST facility. You see here the roof of the accelerator part is removed, And you see here the synchrotron, the transport lines, and the superconducting gantry, like the one that you have seen before as they appear. And I thank you for the second time today. And this is the end of my second lecture. I stop sharing. Still, I can't hear you, but I see that Jota is thanking. Okay, so I hope that
thank you very much, Maurizio. Thank you. That was very
enjoy the presentations, and
very useful.
Questions I'm ready to answer.
Yeah.
And if you want to stop me just because you have to go to lunch, then tell me and I will stop talking. Jota, is up to you, so make a sign and I will stop. Okay, you can switch me off any moment. You can even kick me out of the, of the Zoom if you wish. Okay.
Hello, Maurizio.
Cyclotrons produce high energy particles. We need to use degrader to achieve clinical used energies. The disadvantage of degrader is that it will increase the emittance and momentum spread of the beam, which is beyond the acceptance of the beam line and gantry. Because of this, for low energy beams, we end up having transmission in the order of 0.1% from the cyclotron to the patient. How to improve the transmission in cyclotron-based particle therapy facilities? The problem is not that, yes, is the transmission, let's say, between the exit of the cyclotron to the patient. And I don't have solutions. This is really a limitation of the cyclotron, in the sense that we always want to treat tumors at different depths, to scan different depths. To scan depths, we have to scan energy. Because of Bragg peak, energy depth translates into energy. And there is no way in a cyclotron to change the energy inside the machine. There is no button to change the energy. While it is easy to change the energy in a synchrotron, there is a button, there is a way to change the energy in the synchrotron, out of the synchrotron, and there is an even easier button to change the energy out of the linear. So I don't have solutions. For cyclotrons, we have to accept this level of losses, which is very, very, very a concern from the point of view of radiation protection, because it's the only way to change, to scan the energy of the patient. Why is the heavy ion therapy gantry so big? Yes, because of the higher energy of the ions and of this factor 2.8 in magnetic rigidity, which is a factor 2.8 in the size, in the linear dimensions of the gantry. So, and this is something that we cannot beat. The only way is to make the field, magnetic field higher, thanks to superconductivity, going to superconducting magnets. Do you use protons in pulses for your therapy treatment? Yes, protons, they always come in pulses, in bunches, and the bunches are grouped in trains of bunches in pulses. And you can usually always change the length of the pulse. It's an easy way to modulate the intensity of the beam. Question 4, is there any Coulomb interaction between protons which we need to take into account while accelerating and focusing them? Yes, the Coulomb interaction is what I called the repulsion in my previous lecture. The Coulomb interaction is an interaction due to the electric field, but we are in a sense lucky, because also there Einstein comes to help us, because as we accelerate, the faster the particles go, the lower is the repulsion. Because when we accelerate towards relativistic speeds, then the particles create a magnetic field. So you can think, if you remember maybe you have learned at school the Biot-Savart law. If you have two wires of current going in the same direction, you have always attraction between the two wires, right? If you think of two protons, for example, in an accelerator, they are two currents going in the same direction. They generate a magnetic field, and there is an attraction, which is, of course, zero when the particles are at rest, but is higher and higher when you go towards relativistic speed. So, yes, Coulomb interaction is a problem, but particularly at low energy when there is no when the particles are not relativistic. When the particles are relativistic, there is a magnetic effect that comes to compensate the Coulomb repulsion. Okay, I go to question number 5. What do you mean by beam loss? Where does it go and is it dangerous? This is a very good question. Yes, beam loss. So we want to create and transport about 10 to the power 13 protons in accelerator. So it's huge. So we are relatively good. So we spend some time in making a good accelerator, but no way. I mean, some of the protons will be lost. Will be lost because they are at the edges of the bunch, and because the forces mainly are not linear in the accelerator. So if you have an accelerator with only linear forces, it is easy. Forces are often non-linear, and sometimes you have some particles that escape from the bunch, and they are lost on the walls of the accelerator, on the metal, where they can create some radioactivity. So radioactivity means they can activate the walls of the accelerator. And this, for example, it is why you cannot enter an accelerator while it is in operation. It is always locked and protected because of the possible radiation from loss of particles. So we designed our accelerators to minimize always beam loss, because this is harmful for the environment and because of the radiation. And and there are always protection systems just to avoid that this can be a problem for the persons operating the accelerator. But the beam is simply lost in the metal. The proton, it is lost in the metal of the accelerator, the beam loss. How do you treat the residues in the body after proton or ion therapy? I don't understand this question so much. What is residues in the body? Maybe it's no, but the proton, the particles actually cross the body, and then when they are at very low energy, then they remain there. It is only an electric charge, is nothing particularly harmful. So I hope that this was the sense of the question. 7, is there any new technology that makes particle therapy affordable to low-income countries? The way to do is to start with proton therapy. Proton therapy is more affordable, it's less expensive, and for this there are industries that are really working at making proton therapy more affordable, but it is still a long way. And again, the way to go is superconductivity. But one problem that one would face is how to operate a superconducting system. So, okay, in a low-income country, so this is a high technology, but there are ways. Definitely, we are going to work on that. There is people working now on making radiation therapy more affordable to low-income countries, and the time for particle therapy will come, but not today. I mean, it's not for today, unfortunately. Superconducting entry will give many benefits, but it will give a non-round beam at the isocenter. This is a very, very specific question. This is something that, okay, it can be solved. So I know that our experts are working on that, but I don't know exactly what are the solutions they propose. So contact me by email, and I will put you in touch with our experts to answer this question. What about boron neutron capture therapy? This is an interesting application of accelerators to produce neutrons that then can treat different type of cancer. I think it's promising, but from the point of view of accelerator, it requires quite a complex accelerator. It's a complex technology and cannot be coupled with so easily with particle therapy. So this is why I kept it outside. I had a slide in my lecture that I removed yesterday when I wanted to simplify. So again, the person can contact me to have more information on that. In complex accelerator, the energy produced from the collision of particles, where does it go? So in a complex accelerator, you mean if you have a collision of two particles, one or the other, the collision goes into changing energy into mass, E equal mc squared. So the energy changes into mass and produces new particles. The famous Higgs bosons were born in this way by changed by the energy generated in high energy collisions. Question 11, why are alpha particles not used instead of protons for proton-like therapy? Why is the gap between protons or heavy ions starting to become? So this is, again, this is what Manjit Dosani said already, is mainly historical, why we use only protons and carbon. But now we are working for history. We want to also to make experiments and test with alpha particles. We want to test new ions. So we want to bring ion therapy out of history into becoming really an optimized system, but this also takes time and even machine time on accelerators to make tests with different type of particles and really see if we can reach an optimum. And it is true that alpha particles might be an optimum between protons and heavy ions, could keep the advantages of both, but to be proven and to be tested. How do you get rid of the heat energy produced due to the acceleration? Okay, very good question. Also, when I give lectures on accelerators, I tell people that basically, from the energy point of view, an accelerator is like a big water heater. All the energy, most of the energy, 90% of the energy, even more, 95% of the energy of an accelerator goes to heating water. And only a little bit goes to the beam. So from the energy point of view, it's like a big water heater that produces some beam as a kind of a side effect. But it's a concern, and there is a lot of work going on now in the community of accelerator builders to reduce the heat dissipated, to minimize, to increase the energy efficiency of accelerators, and to find ways to recycle the accelerator. I don't see more questions. No? Okay.
Thank you.
I see.
Yeah, thank you very much.
Again, so thanks to you for your attention. I'm sorry for the problem with my audio.
No problem. Thanks to all the speakers. And before closing, some comments. There have been questions via email on the certificate of attendance, and we will